The last section in this Unit 2A is going to be competing function model validation. And so essentially what we mean is when you have a choice between different types of models, linear, quadratic, exponential, how do you choose the best one? And how do you validate that it was the best choice? If we're going to make an estimate, we need to know how good of an estimate that is. And so that is what we are going to look at today. Okay, so we have talked about linear, quadratic, and exponential quite a lot so far this year. We've looked at this in terms of rate of change. We've looked at their form in terms of an equation, and we've talked about what their graph looks like. And so on the AP exam, you're often going to be asked to choose which of the models is going to be the most appropriate given a particular set of data. So let's kind of refresh really quickly on what we know. So a linear function, and now when we're talking about data, it's never going to match exactly, but we're looking for a pattern that is relatively close to this, okay? So linear data is going to follow a roughly linear pattern, meaning like a line of best fit would be the way that we would want to model the data. So here is an example of a table, and remember that what we looked at when we've looked at linear before is we're looking for a roughly constant rate of change over equal value input intervals. So my x's are all counting by twos. I've got that. And if I look at the rate of change here, this one would be plus 1.6. This is going to be plus 2.4. This is going to be plus 1.4. This is going to be plus 2.3. So it's not exactly the same, but it is roughly about the same amount, somewhere between 1.5 and 2.5 all of the time. Is it perfect? No, because its data is very rarely perfect. But so if your data model's a relatively constant rate of change, again, over equal input intervals, otherwise you would need to look at the full average rate of change using the formula. Then you would choose linear. If your data shows that our rates of change are increasing or decreasing at a relatively constant rate, and again, that means our second differences, so you would look at the betweens and then the betweens a second time. And if the data is following a roughly U-shaped pattern, again, not going to be perfect, but that's how you're going to know that it should be quadratic, okay? If I look at these rates of change, I can see that these rates of change are not constant and they're not close. I'm decreasing and then I'm increasing. So then what you could look at again is the rate of change for the second differences, or the rate of change of the rate of change. And we can see here with these second differences that they're roughly between like 2 and 3-ish. So they are following a much closer pattern when we look at the second differences. And the fact that my values decrease and then increase is a good clue that it's going to be quadratic. Does it have to be just because it decreases and increases? No, it could be any other polynomial that decreases, increases, and then keeps going after that. We don't know. But looking at those second differences there helps us know quadratic is probably a good estimate. Okay, exponential is what we've been working on in this unit. So an exponential model will be when the output values are roughly proportional. So that means that each successive value is the result of multiplying, basically. And if we look at this table here, 0.5 times 2 would give me 1. 1 times 2 would give me 2, which is close to 1.9. 2 times 2 would give me 4, which is close to that. We can see that it looks like we're doubling every time. And again, we know what an exponential graph looks like. That is getting steeper and steeper as we go, in this case, exponential growth. Okay, so that's how we're going to decide. So the first thing we might want to look at is graphically, how could we decide? So if I look at example 1, the first thing I'm going to do is plot all of the dots. Pause your video and do that right now. So you get something that looks like this. And so we're trying to decide if linear, quadratic, or exponential is the best model. And that looks pretty darn linear to me. So that is what we would want to go with here. I could draw roughly a straight line that maybe doesn't exactly hit them, but it's going to be very close. So linear is what we would want to use, okay? Go ahead and pause your video and graph the points for B. Here is what this looks like. And so with those values that increase and then decrease, it looks more like a V shape, but we're not going to use that, but roughly quadratic, maybe it could fit somewhere like that. That's not a great drawing, but you get the idea. So quadratic would be the best for this one. So pause the video, take a moment to do C and D and see if you can decide what those are. I'll be back in 3 seconds with both of those answers. All right, hopefully for C, you can see that this data appears exponential. Again, if I kind of follow the direction of these, we're flattening out. This is going to go more like this. And so it does look roughly exponential. If you look at the data, it looks kind of like we're dividing by 2 roughly every time. So exponential is probably your best here. Now on D, the graph looks like this. And we might look at this and say linear. But if we look at the rates of change on this table, we can see that we don't have this constant rate of change. We have an increasing rate of change, which could lead to quadratic, but without having more information, we don't know for sure. We could also look at these values, and if we look at the ratio is about 1.5 each time. So 2 times 1.5 would be 3. 3 times 1.5 would be 4.5. And if we keep going that way, exponential might be better. It's kind of a slower, more gradual curve, but I would probably guess exponential on this one. But if we're not sure, then how do we choose which one is really going to be the best model? Well, we would look at both and we would use technology to help us decide. So let's come back to this idea of residuals that we talked about in the previous unit. So whenever we're creating a model, our model is going to predict whatever your dependent variable is, your output for that particular input value. And that's not necessarily going to be the same value as the actual data if I observed in real life and collected the data. So we have to remember that our value is not the guaranteed value. It's only the predicted value. And if we're going to make a prediction, we want to know how good that prediction is. So remember that we talked about before, the residual is the actual output value, so the piece of data you collected, minus the predicted output value using our model. Now, again, if you want to check the residual, it has to be against data you already have. That's how you would check it. You can't go against predicted data if you don't have a real value to compare it to. And remember, I told you the way that you can remember this is we are taking an AP pre-calc class. So that is the order we subtract in. Actual minus predicted AP class. Okay, let's revisit this example here about the weights of newborn babies. We did this back in Unit 1 in section 1.3. So we've talked quite a bit about how to use a regression model. Let me make this smaller so I can fit the whole thing on the screen. We've already talked about how to use a regression model and using a graphing calculator. If you need a refresher on those instructions, go back to your 1.13 notes, okay? So it says the weight of newborn babies can be modeled by a linear function for the first 4 months after birth. Selected values of the weight in kilograms of particular babies are given in the table above, where T is the number of months since birth. So when we did this before, we used a linear regression, in our calculators. And the model that we found was W of T, because that's the name of the function they gave us, is 3.34 plus 0.8 t. Now, again, your graphing calculator used x and y, but the function they gave us was t and w of t for our independent and dependent. And then we used that model to predict what happens at 2.5. So w of 2.5, you're just going to put that in your calculator where hopefully you've stored w of t. And what we saw, again, we did this before, was that we get 4.34 kilograms as the predicted value. Then we looked at the residual. And so the residual here, because we did approximate some values up here, and actually they gave us an actual weight. So they gave us the actual weight of the baby at 2.5 months was 5.5 kilograms. So that is the actual amount versus our predicted amount at 2.5 months, which was 5.434. So what we looked at before was just calculating the residual, but now we're going to interpret this a little bit more. So the residual is going to be the actual 5.5 minus our predicted, which is 5.34, and we get 0.16. But now the new question is, does this tell us that our model underestimated or overestimated the weight of the baby? And since this is positive, the actual minus predicted, if I do A minus P and I get a positive number, that means that my estimate was less than what the actual value was. So we underestimated in our case, okay? If the actual is bigger than the predicted, we're gonna get a positive. That means our predicted value was less than the actual value, so it was an underestimate. If I do my actual minus predicted and I get a negative, that would mean that my predicted value was bigger, so I overestimated in that case. So that's how you can interpret what your residuals do. And even more than that, and what they're often going to ask you to do on the exam, is they're going to give you what is called a residual plot. So if for that baby bird, or not baby bird, that's a calculus problem, for the baby weight problem, if I used my model to calculate the residual for each of these data values that I've been given, and then I plot those on the graph. At t equals 0, my residual was blank. At t equals 1, my residual was blank. Then you're going to get a scatter plot of graphs kind of like this. And so we're looking at a 0 residual would be perfect, and then we're either above or below. And so here is what we expect to see. If I look at the residual plot, and on the exam, they're not going to ask you to make the plot, but they're going to give it to you. So if they give you the residual plot, if the model is appropriate for your data, meaning it's a good fit, then you should not see a pattern. So the example right below here, those dots kind of just bounce all over the place. I would say that's not a pattern. If we see something that has a clear pattern, like a straight line or a quadratic or something, then that means that our model was not a good fit and we should have tried something else. So in the case of this example D here, we could find a linear model, look at the residual plot, find an exponential model, look at the residual plot, and that would help us decide better which one is actually the correct model. So if we look at example 3 here, it says we used an exponential regression and the residual plot for that regression model is above. So which of the following statements is true? When I look at this plot, those dots are scattered everywhere. So to me, that means that there is no pattern happening. So that means that my exponential model was not appropriate. And read through all of the choices, but we can see that that is why A is going to be the right answer. It's not an appropriate model because, I'm so sorry, that is incorrect. It is an appropriate model. The model is appropriate because the residuals have no pattern. No pattern means good, okay? If my residuals follow a pattern, that means there was a pattern in the original data that I didn't see. So that's why we're looking for no pattern. And this last example here on this page, it says a group of students used the set of data to create linear, quadratic, and exponential models. After they did these 3 models, they made a residual plot for each, and they're trying to decide which one was the most appropriate. So if I look at the first one for the linear, do those values follow a pattern? It's not necessarily linear, quadratic, or exponential, but they definitely do follow a pattern. I can see a clear path that those dots are following. So linear probably wasn't great. Quadratic, I can also see that these roughly follow a pattern. So even though it's not the 3 that I talk about, that's probably not going to be great. But exponential, I've just got dots kind of everywhere. And so that would be why exponential is the best model. And so here is how you would want to answer that question. It's exponential since the residual plot for that model shows no pattern. So you can pause and get that copied into your notes very quickly. That gives you the idea. I'm not going to work through this last example on here, but I would like for you to take a second to think about that and then pull up the PDF notes and make sure that you get the correct answer and information down from there. That should be everything that you need to know. I will see you later.